So I've updated the Gus 2 book some, and want to show you what's in it and what I've done. Nothing major, just added a little bit here and there. And today I want to go through and look at a video so that I know that that's always questionable whether or not I should do the videos online or not, but I don't think they'd mind. But uh, so. This is what you've had so far. And again, a lot of this came from old Sham's outline books on these various subjects. And then I want you to understand that you're not going to be held responsible for a lot of this stuff. You're not going to be held responsible for just about any of this stuff. But I just wanted to let you know that, especially the transfer lines, the transmission line stuff, no, and this, no. Um, the the best thing that I've found so far to teach you is this stuff down here when we got into these there's Maxwell's equations. I finally put them in, but the transformer area where we looked at um, this I found the other day, and this is very good. It's the Bussmann. Um, it's the basic equations for the calculations that the guy that we did the video on, he went through and did, but he was doing his based on this. These are the basic equations that he was using. So you find your current, your secondary current. Yes, sir. Got it. Well, that's a problem. We'll get it. Sorry about that. I was so concerned about this, I forgot about that, but we'll get there. So this is added, and it's in page 48, 47, 40, 48 of the of this text. And it is becoming a text. As you know, as I go through this stuff, I'm actually building what amounts to a text. It's my own text, but you can use it if you want to. And if you get into a question about how to find the fault current, right here are the basic rules. So starting on page 48, these are the Bussmann basic rules for following how to find the fault current in a circuit. Okay, and three-phase circuits and three-phase faults right here. And there are the calculations and there's examples. So that's a very, very powerful way of looking at it. Now, I've got other ways of looking at it as well, but this is the best that I found. That is by far the best. And then you go through these reactance tables, and then we go down here, and then we get on to the actual thing that what I found when I was doing this from the point of view of this guy right here, these calculations we kind of did in class, and then I gave you some other numbers and you did those. But this right here is some of these examples are what I would use. And unless you can find something better, use this approach that is having to do with finding the fault current and the secondary current on a transformer in a factory. So the calculations that this guy went through are golden, and I would use these to the best of my ability as a general rule. So again, these are approximations, but he goes through a lot of different scenarios, and you can't beat this. You can't beat this video. And I basically hacked the video up and put it in here, and then I ask you to do this as two homework assignments. Okay, so that's that. Okay, and anyway, there's a bunch there. Now those should agree with that Bussmann thing up above, and I haven't checked to make sure that they do, but they should. But this is the better of the two. Okay. So again, I put that in there, and two transformers in series, blah, 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 and all that kind of stuff. And then the motor analysis. Now, um, what I'm going to do next is, and this is the summaries of some of the stuff that he did. Okay, basic rules of thumb. So then we did these, you watched these 4 videos, and you handed in half a page each for those. So those would be, those are homework assignments or whatever they are, but those 4 assignments, those 4, and I'll get numbers with these, but basically that's the next thing to do, okay? And then this, which is another example of fault analysis, which is the same as the busman, which is the same as the guy that just did it, but this is another example of the same thing, just explained a little bit differently, but it's the same thing, okay? Same thing. And here is from 2 sources coming together, what would be the fault? It's additive, and here's an example of that. And down here is some more. Now, here are the names of the 2 software packages to do a 1-line, and this is either one, and I think you can probably utilize this one. I think you can get a 30-day or something like that, because I'm going to ask you to do a 1-line. It doesn't have to be as good as the ones that they do professionally, but I want you to do that. Now, how do you find out how to do a 1-line? Well, here are all the symbols for a 1-line drawing, okay? So I'm not going to say how many of these symbols you have to use or how many to draw your 1-line, but these are the symbology. This is the symbology that you need, okay? So again, I'm going to pretty much leave it up to you, but you're going to have to do a 1-line. If you get the ECAP or the other one as a download, then you can use these with that and then draw it yourself. Okay, now this is what I wanted to do today, and listen to this, but then I also wanted to, I'm not going to, this is again, power systems with the symbology and all that kind of stuff, and it shows you again, this is that, this shows you how to manually do these calculations, and it is the same thing as the guy did and as the busman people did. This is it again, but this is from the Shams outline people. So again, you get the same basic thing. Again, how to calculate through a transformer, how to calculate the fault currents, and there they are again. This is the Shams outline of the same thing. So I found it about 3 different places, 4 different places. Which one is the best one? I don't know. But I think you probably now know that I'm serious about this aspect and the thing with the guy from that he did that. And this is some more pictures with the same stuff. Again, I'm not going to test you on this. It's not like I'm going to make your life miserable. But as you take this stuff out from here, and if you get a job with the power company, they're going to probably present you with some of this stuff, and maybe this is something that you can reference and you can go back to and say, now, he explained it about 3 different ways, or he kind of explained it this way, and this way. Which one is the best one? And they're going to show you what they want you to do, or how they want you to do it. And my suggestion is, or my thought is, they're going to make you do it based on the guy from Eaton, but they might also throw in these imaginary numbers. I don't know. I do not know. Good question. Don't have an answer. And this is another example of getting the short circuit current rating, SCCR. Okay, so this is another example of what you did with the those 4 videos that you evaluated. This is another example of that, and this one does not turn out so well. And let me talk a little bit more about fault calculations, types of faults, and I'll go through that a little bit later. But this is toward the end, and again, more information on faults. And I want you to have a good idea about faults, because we want you to be safe, and that's what today's thing is going to be about, okay? So again, more calculations of faults, more, oh, and this, by the way, is a very complicated example of 4 bus bars, okay? So you got a bus bar here, you got a bus bar here, you got a bus bar here, and you got a bus bar here. You got current in, current out, and you've got crossing of these bus bars. So you get these motor control centers. So here'd be a motor control center, 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 and here's the cross feeding between them, and here is your admittances between them. And now from that you can find the current available in 1, in 2, in 3, and in 4. So that's your I1 through I4. Okay, and there's how that's done. Again, I don't want to try to depress you or impress you or whatever, but I do want you to understand that it's important that you know that that stuff exists and you can do calculations based on it. So again, what I did this morning was I asked ChatGPT about 110, 115 volts AC. Is it considered hazardous? In other words, do you have to wear protective clothing if you open a panel with 115 volts AC? And they say yes. Now, why don't I just buy this NFPA 70E book and bring that out and show you that and say, you know, there it is in there. Well, that book costs $180. It's a little thin book. They make their money based on the selling of these books. And I bought one in 2012. I refused to buy it again, so I used ChatGPT to tell me the information that I need out of it. Whether or not it's true or not, I think it is, but it does say what? It does say that you have to have clothing on that is protective if you even work on 110. So if you work on 24 volts systems, you do not. So at 24 volts, you're protected at 115 volts, even though everybody says, well, we've been doing this for years. It still is applicable. So I'm going to show you a video of this, and this is another video, I know, but I want you to hopefully get something out of it. Okay.
Hi, folks. Thanks so much for joining us today for our Safety and Health Magazine webcast sponsored by Tyndale. We're going to give our audience just a minute to get settled in, and we will be with you
I want to get this larger if I can.
shortly. Thank you.
There you go. Thank you. There you go. So let's see if I can get going.
A big thank you once again, everyone, for joining us today for our webcast. We're going to give our audience just a few more seconds to settle in, and we'll start the presentation shortly. Thank you.
So this is another version of the one that we had from here that showed all the arcs and sparks. But this is a little bit more up to date. That was about 15 years ago. That was filmed about 15 years ago, 12 years ago. This is more up to date. This is fresh.
Well, a formal hello to everyone, and welcome to today's Safety and Health Magazine webcast. OSHA's new arc flash guidance, major implications for de-energized and low voltage work, sponsored by Tyndale. My name is Barry Botino. I'm an associate editor at Safety and Health and a co-host of our On the Safe Side podcast. I'll be your moderator for today's event. Before we get started, I want to share a few housekeeping items with you today. First of all, the views of today's speaker and organization are their own and do not necessarily reflect those of the National Safety Council or Safety and Health Magazine. Any mention of a commercial enterprise, product, or publication does not mean the Council or the magazine endorses those items. At the conclusion of today's event, we'll conduct a Q&A session with our speaker. If you have a question at any time during today's event, just click on that Q&A button, which is located at the bottom of your screen. Type in your question and tap the send button. After this presentation, you'll be asked to complete a brief evaluation survey, but I'll tell you more about that a little later. Finally, this webcast will be archived. If you want to view this presentation or any of our past webcasts, please visit safetyandhealthmagazine.com/events. Now let's introduce our speaker. Joining us today is Scott Margolin. Scott serves as the Vice President of Technical at Tyndale, where his 35-plus years of experience in arc-rated clothing provide.
So why are we doing this fault current thing, and why are we trying to figure out short circuit current rating and all that kind of stuff? It's right here, and it's because you need to figure out whether you need to wear that rating or not, that rating for the clothing. So again, I was curious today if you absolutely had to, if you had a 110 volt panel, do you have to wear the clothing? And the answer is yes. Okay, all right. So do you follow now why a lot of people are switching to 24 volt controls in their panels? So you don't have to. So you can work hot, but without having to wear that clothing. So if you now look at where are we at, I think a lot of people are going to 24 volts as a control voltage. 110 has been there for years. What's the disadvantage of going to 24 volts? Well, if you got a long run of wire from it, then all of a sudden your wire gauge might go up. So you got to calculate now that wire gauge that's different. So this part of it right here, it is really catastrophic if you graduate from here and walk out into industry and walk into a plant that does not appreciate this and you get hurt. I've not had any student ever get hurt to the best of my ability, but it's possible, and I don't want that. I want you to not get hurt. Like I said, I think I was very fortunate that I never got hurt because I did some dumb stuff. But the other thing that they didn't mention is falls, and that they don't talk about falls. But if you get electrocuted, if you get shocked, and it doesn't have to be much, you first of all react, and if you're on a ladder, you fall. So they don't talk about that here, but that's the other brother that comes along with this, and that is if you're on a ladder and checking something out, and even if you get a small shock, I'm not saying 24 volts will give you that bad of a shock, but it can give you some jolt. And I don't want anybody to get shocked, but I've been shocked with 110, and it rattles your, as they say, it rattles you. But anyway, let's go back. Anybody have any, today was just basically, all right, this is Wednesday, and I definitely want us to do another one of these. So this is the quiz. Code quiz. We didn't do 308, did we? 309. Let's do 308 and do 309. Okay, so what would be this one? 308. Did we do this one? Okay, let's go to 309. 509, excuse me. You need to hand these in too, by the way, because it's something to grade you on, and I I really do want you to get this. You done this one?
It's similar to the other one, right? Can't make a selection.
I'll tell you what, I'll let you fill these in and hand them in. So this would be, you need to hand in 508 and 509, those two. And those will be two more homeworks to do, and I'm going to get this organized, eventually get it organized. The other thing I want you to do is, between now and the break, is one, not just one more thing, but one more thing between now and the break is to do a one line. So whether or not you do a big fancy one or whatever, use as many of the symbols as you feel that you can, and you can either draw it by hand, or you can use the software from the software that's on here is let me see, this software package back here. I think you can do a 30-day download of it, and you can at least try it and see if you can get it to work a little bit. I want you to do a one line. And well, this has been fun. I don't want to complain to you, and I know you probably can complain about me, but I started with this whole thing this year knowing that I did not have any of this stuff really developed, and I'm sort of like doing it as we go. But after the break, we're going to do motors, and I'm more familiar with motors, and I know a little bit more about what I want to do there. But okay, so today was this Tyndale, and then up here are the two types of ECAP and SKM, and I don't know if either one of them can be downloaded for 30-day trial, but I want you to try to see if you can download one of these, or there may be another one, but do a one line and hand it in to me, and that will be for a grade as well. And I'm not going to say for sure, but if you promise doing all that kind of stuff, and we get through to midterm, maybe we won't have a in-class test. We might have some kind of a open book, maybe a review or whatever that you can do open book and that type of thing. But as far as a in-class test, I probably will forego that. If you do all these parts and pieces, and I don't want to have to make up a test, is what it boils down to. Because I don't know exactly what's the best, but I want you to know how to do a one line. I want you to know how to do a fault calculation. I want you to know how to find an SACR, and I want you to know when to not go into a panel live, and the rationale why. And if you can do all that, you can go into a control room, into a factory, and you can survive. Okay, and you'll be okay. I don't want anybody getting hurt. Before you go, one of the very first things that ever happened to me was I was working at Libby Owens Ford, and I had no idea what was going on, but and this has to do with a DC motor. But at the time, there was no guarantee that they didn't have all these elaborate circuits for the field of a DC motor. So they had this big DC motor doing something, I don't know what it was, but I don't know, it was maybe 100 horsepower, 200 horsepower motor. But if you lose the field, if the field voltage goes to zero on a DC motor, it starts to wind up. I mean, it just starts going faster and faster and faster and faster and faster until it breaks up, until it explodes. But it gives you a little bit of a warning because it goes, it does that. And if you lose the field on a big motor, a big DC motor. So it was in a control room, and I don't know what happened, except for there were a bunch of guys in that control room when it started. They lost the field, and evidently it started this wind-up process. And yeah, they all dived to get out of the room before it exploded. So they did a big, everybody ran for their life, and they did, and they got out, and they were all patting themselves on the back because they all made it out. What did I get in? What did I get into? But on the other hand, I say that doesn't happen anymore. We don't have that. That's not a problem. No problems like that ever exist. It's real world. They do. So don't ever underestimate. Another thing I want to tell you about before we stop, and I want you to understand that there's a million of these stories, but this is another story that happened. One of the guys I worked with, one company, had severe ear damage. And you say, how could you ever let that happen in a plant? And how low can you hear frequency-wise? About 20 hertz. And this was 10 hertz noise. Very low cycles per second noise. But it was very high intensity. He said, I felt very uncomfortable, but I couldn't hear it. It almost destroyed his hearing. So again, there's a million of these stories, but ladders, low frequency noise, are just two of those things you think, what, you know, what on earth? There's more ladder stories than you would believe. Ladder stories and then shock stories. These guys are talking about shock stories and burn stories, but ladder stories, anyway. The low frequency noise story, it's hard to believe, but that one is true. I know the guy.